I'll go ahead and start. First of all, that was a fantastic talk that came before, something more on the engineering side of data curation. Unfortunately, this talk is a bit more scientific. I'll be presenting my recent paper that's been going to be published at CVPR, which is the top conference for computer vision. And it's a paper about batch sampling that improves pre-training for multimodal models such as CLIP and SigLIP. And this is a large collaboration that we've done with many different places, as you can see here. And this is the team that we built, and I'm really grateful for all of these people who've helped me a lot along the way. Uh, this particular work is related to data curation, data recycling. So just before I start my presentation, I thought it'd be useful if I share like the broad themes that I'll be discussing today. So if please stay tuned and please ask questions if you're interested in any of these particular axes of data curation. So, to begin with, and maybe everyone here understands why it's important, I thought I'd clarify why data-centric research is important. A lot of companies and a lot of labs do a lot of work on methodological advances where they build a model from scratch and they really focus on what components these models have. But this is not enough. And in addition to just scaling the model size and the data sets you train on, these don't seem to be enough, and we as a community have agreed that pre-training data is an equally important lever to pull. And this dataset design really affects how to train models, how these models generalize, how robust these models are, and how well they can tackle edge cases or, as I said, long tail coverage. But because the scale is so large, there is no control over these web scale pre-training datasets because they can scale up to like a billion or even 100 billion samples. It's impossible to manually control them. So prior works have done quality measures at scale to score data samples and then filter them based on some score or some metric. And in general, this is the pipeline where you have a raw web pool, you curate based on whatever function or whatever model you treat as a teacher or a quality model, and then you end up distilling the better quality data into the model that you train. And this matters for CLIP, which is the focus of this work and this talk. CLIP stands for Contrastive Language Image Pre-training, for those who don't know. This particular framework learns from relative comparisons within batches. So all of these models get a batch of data at one given time, and the composition of these batches are really, really important to train CLIP models. So in CLIP, we ask what is in the batch as a very important question because it really determines the composition of these batches really determine how well these models perform downstream. Therefore, as I said, it's not just something you think about when you do the data loading, but it's an actual modeling choice and something that people should really focus on to get right, to actually get better models that perform well. So, in summary, the current ecosystem of curation is a bit of a mess, if I'm being honest. First of all, it's offline and it's static. So once you do the filtering, you get a smaller data set and then there's no going back. So you have to train on only those samples. There's a lack of reuse or a lack of recycling, which we argue in this work that is important. It's concept agnostic, which means that it only looks at a data sample as a sample, as an image and a piece of text. It doesn't look more deeply into the semantic composition of these samples, like what concepts or what objects these samples have. So it's not fine grained and it's at the sample level. And I would argue that it's black box in that whatever model you use to filter or you score these samples, you end up taking the biases of those models as well. So whatever the training regime for the best quality model is, those biases are induced into the data sets that you create. And of course, to summarize all of it, it's a one size fits all regime where it's fixed, it's not flexible, and it ignores what different tasks actually need, which are very divergent, and something that I'll focus on in my talk today. So when we have this problem of the current curation regime, we kind of took a step back and thought about how to actually compose the data sets. And we look at DataConf, which is a web scale pre-training data set. We look at the 128 million scale dataset version of this, which contains basically 128 images and text pairs. And we decide to densify the supervision instead of use a model to score and filter samples from this dataset to have a better quality dataset. So overall, it kind of looks like this, and I'll talk about each component one by one. First of all, we start off with DataComp, which contains image and text pairs. And we build something called a concept bank from several sources. We actually curate the largest open source concept bank with about 20,000 concepts. And these concepts are mostly nouns, such as like man, woman, flower, that exist in the natural world. And it can be very fine-grained, it can be very broad, but it's very holistic and it encompasses a lot of things. Uh, what we do with this current pool is we start tagging images. We completely focus on the images for now. We have a fantastic model called RAM++, which lists a set of concepts that it believes should exist in this image with a certain confidence. And we use that as our starting prior. But since this concept list is very susceptible to hallucinations, it's not very safe to just take this at face value. So what we do in addition to that is we ground them. So by grounding, we focus on localizing these concepts in the image. And by doing so, this adds a second layer of supervision and it makes sure that it's actually there. These concepts are actually there in the image. And as you can see here, we can successfully kind of filter out hallucinations or concepts that can't physically be grounded in the image. And we take this final list of concepts as kind of labels for these samples. And what we do with that is another step, what we do with this is we recaption kind of poor alt text or original text from the internet to make sure that it supports the concepts that are there in the image and actually reads quite well, to be honest. So we use a Tianwen 2 model, which was state of the art at the time. And so completely the final artifact is an image, an original caption, a list of concepts with their bounding boxes, and a better quality caption. So this is our data set that we curate. And these are some statistics about it. It's 128 million samples, 12,000 unique concepts that we filter out from the 20,000 concepts from the concept bank, because not all of them were able to be successfully detected in the images. And across the 128 million samples, we have about 500 million annotations, and with a median of 3 concepts per image, and we have high quality concept aware captions. So the objective here is metadata. Have this metadata per sample, and we can actually use that for curation, and it can be reused in many different ways. Some more statistics that might be useful to data-centric people in the room. These concepts are extremely fine, extremely long-tailed. So the plot on the left kind of shows that there are very few there are very few concepts that are very well represented. So most of them, about 97% of them are not that commonly found in these data sets. So they have a count of maybe less than 1,000 or 10,000 in 128 million samples. And on the right here, we kind of show that the number of concepts per sample, so to show how complex images are kind of left skewed, so they're generally very simple. So in general, they have about median of 3 concepts that have been detected per sample. So in general, the samples are quite simple and they have mostly common concepts such as man or woman or flower in the general pool. Some more statistics about the captioning. We kind of show that the original alt text is again very left skewed. So in general, they're very short, whereas our recaptions are more flat. And we kind of balance out with respect to the actual image quality. So we actually balance out the text quality with our recaptions, so actually to keep them at par. We also show on the right that there's a much higher concept adherence. So what we do is we just take the text and we try to match it with the concepts that have been detected for that sample. And we kind of show that there's an exact match of about 4% for the alt text, which means it's very poor. We kind of made it a bit more relaxed to see if there's a partial match. We do a fuzzy match kind of regime to check if maybe 60, like depending on different thresholds, how high does it go. it's still fairly poor. And we show with our recaptions, we have more than 50% of an exact match. And if we keep the threshold at 0.6, we have close to 90% of concept adherence, which is a very, very good resource to have, I would argue. Some qualitative examples in case people are interested. Obviously, because just showing numbers isn't good enough, we show the good quality concept adherence in our synthetic captions compared to the alt text. And we also show some failure cases that the captioning model hasn't been able to kind of adhere to that well. I would argue that with better open source vision language models, this kind of problem will converge and we will have even higher concept adherence. So, given this data set, the kind of question we'd like to ask is, given these visual concepts, how do we use them or how do we modulate across these different concepts during pre-training and tune and like have better tuning for different downstream tasks? So, in short, how do we create better data sets for different tasks? And what we propose in our paper is something called concept-aware batch sampling. And it's an extremely flexible kind of regime where you can, given a kind of rule or a heuristic as we've defined here, any custom function that takes a larger pool of data and then filters it out to a smaller pool of data, you can flexibly design anything you want. And during training, what we do is we take a larger batch. So let's say we want to use a batch size of 4,000. Let's say we call 8,000 samples at once, and we use this particular function to score each sample in the data set and to select the top 4,000 samples based on whatever rule we use. So we've designed cabs to be super flexible. We instantiate two algorithms in our work, which I'll talk about later. But in general, for people who want to use our DataConcept dataset and basically do batch sampling, we've made it extremely flexible to use, and we've publicly released our code, so it might be interesting for people to actually use it. Why should we make it flexible? The argument is that downstream evaluations are kind of different. This is something that was ignored in the past, where people said just pool whatever evaluations you have and see how well models perform. But we've kind of empirically shown in our work that distributionally as well as a task itself, different evaluation systems are different. So we mainly focus on classification and retrieval. Classification in general is like ImageNet classification, and retrieval is given a text and an image, how well can you retrieve the correct text for a given image. So we kind of focus on these two tasks in this paper. And so our goal is to curate based on these given tasks. So in classification, we kind of care about concepts as a concept. And in retrieval, we kind of care about how complex scenes are. Because in general, retrieval data sets have scenes where things are happening. In general, there are more concepts. So our curation should kind of focus on these particular tasks. Yes, so for classification, we instantiate something called CAPS DM for diversity maximization. So on the top, I show like what a standard clip batch looks like. It's super long tailed, and the common concepts are much more prevalent in the batch. Whereas our task, let's say, is to flatten this distribution as much as possible. And given like a hard limit of how many times a concept can appear in a batch, per sample, of course, we show that by flattening it out, we expose the batch to like a lot more, almost double the number of concepts compared to IID sampling. So, like I said before, the main task is to take more samples and then filter it down to whatever ratio that you want, and then train that batch at a given time step on for a clip or SigLIP model. Jimmy told me that I should go into detail. So I've put down the entire pseudocode and I'll talk about them one by one, just so it's clear to everyone. So the task for like the way we instantiate CAPS DM is to make sure that the current state of the batch is a factor. So we use a heap that stores the samples that have already been selected and kind of take the concept counts for the selected samples into consideration when deciding the next sample that comes in. So this is to ensure that we never go above whatever cap we decide for a concept in a batch. And since we build the batch sequentially, it constantly adapts to whatever sample was initially in it. So the initialization is important. And that's where we set this balancing problem that we talk about. For the entire super batch, the larger pool, we define the statistics of concepts. So let's say man exists in the super batch about 100 times, woman exists 50 times, and reticulated Python, which is a super long-tailed concept, exists maybe 20 times. So these are important factors that define how rare concepts are, because we want to uplift rare concepts and make sure they get pushed into the batch earlier, just so that we fill faithfully our batch. So yeah, since we calculate the gain for all these samples, we push the best sample into the heap at the current stage, and then we update the heap and to make sure that the next stages of the sample selection is aware of the current batch as it exists. So how do we do this? We kind of define something called a marginal gain function, where we decide like how much does the sample being selected fix or affect the current batch. So we would score, let's say, a sample that has man and Python in the pool, and you compare it to another one that has BMW Z4 in it. We kind of score the samples high that have valid concepts, that means concepts that have not reached their cap yet, and rare concepts. So we uplift concepts that are more rare, we score them higher so that like the probability of selecting them gets higher. And we score them low mostly if concepts are already saturated. So using all of these tricks, we kind of populate a batch to keep the distribution as flat as possible. So CAPS DM will pop given the scoring for every single remaining sample in the super batch. It pops the highest gain sample, adds it to the batch, and then constantly updates iteratively the concept counts, and the next stage is determined by how the concept distribution is for the sub batch that's being selected. So bit complicated, but I hope I explained it decently. We instantiate a much now that was super complicated. This is super simple. We have another CAPS batch sampling algorithm, which is called frequency maximization, where we basically want to keep the most complex samples being the samples with more concepts in it, into the batch. So literally very simple. Take 8,000 samples, count the number of concepts in each sample, rank them in descending order, and select the top 4,000. In very simple, that's exactly how uh, frequency maximization works. Uh, Now back to the main question we were asking, like, is classification and retrieval really that different? And do our different batch sampling algorithms actually work to adapt the training data that the CLIP and SigLIP model sees to kind of suit these two different tasks? Turns out, yes. What we do, and this is kind of an exciting plot to show, where we basically take the ImageNet training dataset, which is for classification, and the COCO training dataset for retrieval. It's the green and the orange dotted lines, and we show the distribution of the number of concepts per sample, which is the x-axis. We show how well it's distributed in general, and we show a left-leaning tinge for classification and a right-leaning tinge for retrieval, which obviously means that retrieval datasets have more concepts in each sample, and classification datasets have less concepts in each sample. And we kind of show that our two different CAPS algorithms kind of overlap the respective tasks that they try to train a model for pretty well. And so we kind of hope that this kind of distribution matching really helps in training better models. And turns out, yes, it's true. So yeah, we kind of outperform the base setting, which is just IID sampling, where you randomly sample from your large data set. Aggressively, we show very significant performance gaps between IID sampling and our batch sampling algorithm. And note that we change nothing. We change nothing on the model size. We only change the data that the model sees. So between IID and CABS, the only difference is the batch that is fed to the model. Nothing else changes. Uh, so for ImageNet classification, we show results on alt text as well as our recaption data set for both a CLIP model for VITB32 and a SigLIP model for VITB16. The same trend kind of exists for CABS FM. One thing to maybe note is that uh, the recaption data performs much better for both IID and CABS. simply because the text is so much better and it kind of aligns really well with the kind of captions that retrieval data sets have. So in general, having recaption data is just better for retrieval. So yeah, we kind of show that our two different CABS algorithms are optimized pretty well, and the fact that we should make our evaluations more task adaptive, and that should inform how we do curation. I think we sufficiently show that here. In general, some more results is that our gains over IID is broad in that if we expand the benchmarks that we actually test on, we do 28 benchmarks in total, and we show performance gains almost across the board. So this is for VIT S16, this is for VIT B32, which I showed before. This is for SigLIP VIT B16, and this is for SigLIP VIT S SO400M. So we test across many model sizes, as well as a clip and SigLIP training methodology. So we show that CABS works well across the board, which is a good sign. And comparing with baselines and state-of-the-art models, we compare CABS DM with Metaclip. Metaclip is very famous work for data-centric people in that they basically do offline curation at the text level. So they do concept-based concept flattening at the text level. So what they do is they have a vocabulary and they basically select across from 400 million samples. They select in such a way that the concept distribution is quite as flat as possible, and then they train on it offline. We kind of match their regime, and we kind of show that we do better on every single benchmark compared to Metaclip, which is quite nice. Additionally, we compare our results with other online batch sampling algorithms, which are GRIT, VLP, and MAFA. I don't think I have enough time to describe what they exactly do, but in general, the principle is to take a larger batch and and curate a smaller batch that you feed to the model at a given time online. So that's the difference between online and offline. In offline, you create the dataset beforehand and then you train the model randomly picking from that data pool. Whereas in or online batch sampling, you you have an intelligent way of selecting samples as the model trains at different time steps. And yes, for ImageNet and retrieval, we show significant performance boosts compared to IID as well as the online batch sampling. Another interesting thing to kind of show is that the other online batch sampling methods are kind of at par with IID for ImageNet. And even more interestingly, it kind of dips compared to IID sampling for retrieval benchmarks. So turns out we do pretty well across the board compared with online batch sampling methods as well as offline batch sampling methods. An additional result we wanted to show was that can we use these clip models and then fine tune them autoregressively to create VLMs, which can actually generate text, which I would argue is the more exciting regime for these models. And we just take CABS DM and in a very toy setting, and we're actively working on expanding this and making this a bit more holistic and scientific. But we kind of show that we do a lot better than your standard high quality clip model that people have been using all this while with CABS on captioning datasets and VQA. So we even show better performance on the COCO captioning task. So we take 3 captioning benchmarks and 2 visual question answering benchmarks, GQA and MME, and we show across the board we do so much better than like IID sampling. And just to note that these numbers are for the scale at which we're operating on. So this is for a VIT B32 model that has been fine-tuned with a YQNA 7B LLM, which is the standard Lava setting. So please don't take these numbers as like the golden standard. Obviously, the performance is a lot better if you scale up data and you scale up the LLM as well. So just take this with a grain of salt. One of the last experiments we do is a longer training regime. So because we subsample from a larger data pool, we actually expose ourselves to more repeats compared to IID sampling. So for example, if we want to train 128 million samples for 1.28 billion times samples seen, which is a 10-time multiplier, we kind of show that at the beginning we do really well compared to IID sampling, and this kind of corresponds to a 3.2x multiplier. So Your IID model needs 3.2 times more steps to basically match the CAB's performance for classification, and 2 times the number of steps to match retrieval performance. This number kind of tapers out at the end of training because you just simply repeat more samples for CABs compared to IID, and that's where like a totally different axis of influence kind of kicks in, and that affects performance. So I would argue that the first half of each plot is the more useful insight to provide here. And like I said, the gains kind of shrink with extreme repetition, but it's still very competitive. So it still works pretty well. So yeah, some of the key takeaways for people who maybe joined in late or people who are generally interested about data-centric pre-training is focus on concepts. Try to annotate samples being more concept aware. Turns out that that actually works quite well, both online and offline. Online is actually better than offline sampling. So you don't, and it makes it flexible. So you can actually use the same data set and then do different kind of algorithms or batch sampling methods. We showed too, the community is free to try out whatever they want. So you're not wasting data, you're recycling data, and you're making it much more flexible. You should, the main takeaway, scientific takeaway is that you should adapt sampling strategies to different types of tasks. So we kind of classified as classification, retrieval, captioning, etc., not specific data sets within these tasks. So we still keep it very, very broad. We are not overfitting to specific benchmarks, of course. So we should have some kind of task adaptive curation, which is beneficial. And yes, concept diversity works for classification. Please note that. And concept multiplicity, or having complex scenes for training, works well for retrieval. So thank you very much again for joining my talk. I'm open to questions, and if you're there at CVPR, please come say hi. I'm open to questions. I'll keep my screen active for a bit longer.